Good evening. This is Josh McMahon. Myself, along with three other classmates and CM7303 at LSU, are presenting to you with the life cycle assessment of printed buildings. I'll be starting off our presentation with a quick, maybe just a brief overview of differences between conventional and 3D printed buildings from a sustainability life cycle assessment standpoint. Some of the similarities between conventional and three-dimensional printed concrete is they both use water, cement, and aggregate to create the concrete. So very similar process in the way the material is made. Slumps are probably different, just so you can get through the nozzle of a 3D printed versus shooting off the back of a hopper of a concrete truck. Skilled labor is required to do conventional concrete forming and finishing. Skilled labor is required to set up the printing equipment. Skilled labor required to mix your components to create the concrete, and skilled labor is required to install and complete both products. Something to note with the skilled labor, you need the skilled labor to ensure that you're adding the right mixture, the right amount of fly ash, or the right amount of aggregate. Adding too much of one component over another component changes the strength of the product, changes the slump of the product, so you're not going to meet the job specifications. So you need that skilled labor to understand that stuff and understand what they're supposed to do in there. Also, skilled labor is going to be required to do any testing or inspection process before, during, after you pour your concrete. You want to ensure that you do your break test 7 days or 30 days, whatever your specifications require, and ensure that the concrete has met the strength specifications of the project that you're working on. So this is some areas where skilled labor is still going to be required on both applications. Conventional concrete. One key thing with conventional concrete is that formwork is required to place the concrete for the structure. Formwork, for me, can be three different types. So we use earth forms, we use 2x lumber to do formwork, and we also use formwork that comes in on a truck, and we set it up. We build the forms to what we need. We pour the concrete. A day later, we break it down, we clean it up, and put it on the truck and take it to the next job site. So those are the three different forms that we use, all of which require skilled labor, all of which require man hours on the job. Big thing that I want to kind of touch on is the use of lumber to do formwork. This is something that adds carbon dioxide to our atmosphere. Big piece of this is you can't use that lumber forever. That lumber eventually starts breaking down. It starts warping. It's not doing what we intend for it to do, which means we use manpower to throw that lumber in the dumpster. We pick that dumpster up when it gets full, and somebody hauls it off to the dump. This is additional waste in our landfill that we don't need to waste if we could do a different means of pouring and finishing concrete. Safety is a big concern on job sites. Skilled labor is what's required to do the formwork. This is additional manpower. You might be working around equipment. This is where accidents happen. So this is something to consider. Just a quick note, excessive man hours on the job is what increases the price per yard. So when you start thinking about how much is it for 1 yard of concrete, well, how much is it for 1 yard of concrete? How much is it to pour 1 yard of concrete? How much is it to finish 1 yard of concrete? All of those man hours, all of those extra trips, all of that information goes into your total end price. So these are all things to consider when you're comparing conventional concrete to 3D printed concrete when it comes to price, because ultimately in construction projects, it all comes down to the price, right? So three-dimensional concrete printing, or 3DCP. Three-dimensional concrete printing, several benefits to this. The first benefit that I found is there's no formwork required. This is a decrease in man hours on the job, which increases your safety rating on the job, because now you have less people running around, you have less people building formwork, you have less people interacting with what you're doing on the job site. So this is a huge plus. So doing 3DCP over conventional concrete you're going to save man hours, and you're going to increase your safety on the job. Another benefit of 3D CP is that you load your building design into the computer. That computer is then connected to your 3D printer, and you're just transferring your design from the computer to the printer. You think about conventional concrete, you have to transfer your design from your computer or your set of blueprints to your skilled labor in the field. You hope that they understand how to read you hope they understand how to read the blueprints. You hope they understand how to interpret the job specifications and then apply what you need to do. Now, granted, computers aren't foolproof, but the computer is going to give you a much a higher increase in productivity and success on your job site with a reduction in waste. Huge reduction in waste, because now you're printing exactly what you need versus, I think I need 3 more yards, but I really only needed 2 more yards. So this is going to be a much more accurate project, which ultimately is what we want. We want to reduce our waste. The reduction of forms with 3D CP system, this is a huge savings because it takes away wasted lumber from going to the landfill. It takes away from those man hours of building and forming formwork and also hauling it to the dumpster or bringing it back to the truck to haul to the next job site. Labor is required to set up and break down the printing equipment, but this is drastically less than setting up and breaking down formwork. So another added benefit. With the reduction in manpower, this is obviously going to be a lower price per yard for the concrete, which should go into your math when you're ultimately looking at a cost comparison between 3D CP and conventional concrete. If your project gives you the ability to do three-dimensional concrete printing, there's a decrease in carbon dioxide from printing compared to conventional concrete, and I think one of the key components there is the not having a need to have dimensional lumber on the job site, which is adding to our carbon dioxide. So removing that from the equation is drastically going to help. I think some of the life cycle of the concrete itself is very similar. As we go through a building's life cycle and you pour the concrete and you get the maximum life out of that building, we are then able to recycle that concrete. In my backyard, actually just last week, we met with a vendor who is taking recycled concrete. He's actually taking recycled concrete. They're taking concrete from washout pits. They're crushing it. They're turning that into number 3s, which we're using for construction entrances. They're turning it into aggregate that we're able to reuse and prep slabs and do other things. They're able to even make crush and run with this product. So the concrete served its purpose for the building that we wanted to build, but then it also serves its purpose to give us something back down the road, which is a huge benefit to our industry. Something interesting from my side, the three-dimensional concrete printing, there's actually a company in Richmond, Virginia, which is where I live, who is currently building the first three-dimensional concrete printed home in downtown Richmond. And their idea is that they can build more economical homes in Richmond, in an area where housing is in demand for a price that consumers can afford. So they're thinking, and they've paired up with another company who specializes in three-dimensional concrete printing, but they're working on that project now. So a benefit for me is being able to go downtown Richmond, view this building, follow along on the project updates, and I think there's a huge advantage to the three-dimensional concrete printing from a life cycle assessment, but also just from a green building aspect, and excited to see what the next steps are of three-dimensional concrete printing. Okay, my last section. There's different life cycle stages of 3D printed buildings and influential parameters in each stage. So from my research, I found that there are 3 stages to the production of three-dimensional printed concrete. Stage 1 is the production of materials needed to create the concrete for the project. For example, iron production, slag granulation, slag drying and grinding, coal-fired power generation, fly ash drying, sand production, silicate production, ultra-pure water production, and additive production. So this is the first stage. This is where the meat and potatoes are all put together and everything is generated and created. Stage 2 I thought was extremely interesting. Stage 2 is the transportation of the material. If you've been in construction for long enough, you know that you purchase the material, it shows up on the job, you install the material, you go to the next one. This year has really changed my way of thinking on that. Now I'm always worried about where's the material coming from? How's it going to get here? What issues could I potentially have happen? What could derail this from coming through? And do I need to find an alternative means of getting the material, or do I need to go find a different choice for material to accomplish my goal and keep my project moving forward? Stage 3 is the actual creation of the concrete. Stage 3 is the actual creation of the concrete that will be dispensed through the 3D concrete printer. So not very difficult stages for the concrete printing side, but like I said, I think the most interesting thing for me was the transportation of the material.
Hi, my name is Kenneth Doyle, and I'll be taking us through the life cycle assessment, study goal, and scope definitions. Life cycle assessments seek to measure the environmental impacts associated with all stages of a product, such as concrete, or a project, such as a building or highway, from raw material extraction through to processing, transportation, use, and disposal. Life cycle assessments shall include the goal and scope, inventory analysis, impact assessment, and interpretation of the results. The International Standards Association or organization defines an ISO 14044 that the study goal is to include the following: intended application, reason for carrying out the study, the intended audience, and whether or not the intentions of the comparison study are to be disclosed to the public. For our life cycle assessment of 3D printed buildings, the goals are to 1. Conduct an internal analysis of the implementation and impacts construction 3D printing has on the environment, and 2. Examine the differences between conventionally built buildings and 3D printed buildings to understand the change in environmental impacts 3D printed buildings can have on the construction industry. The application of this study is to give students a better understanding of the environmental impacts that affect both conventional and 3D printed buildings, as well as a better understanding of how to conduct a life cycle assessment. The intended audience of this study is for internal use for students and is not intended to be released to the public. This study was done by conducting an attributional cradle-to-gate life cycle assessment that includes extraction of the raw materials to create the concrete, the production of concrete used for construction, and the construction of the concrete building. Transportation was determined to be outside the scope of this life cycle assessment and was excluded from the project. Each of these phases were analyzed and determined what each phase contributed to the overall impact of the construction of these buildings has on the environment. In order to study the environmental impacts of the construction of the concrete buildings using either conventional construction methods or 3D printed construction methods, a functional unit of CO2 emissions per kilogram per meter squared was used in order to compare the CO2 emissions between the two methods. It is to be noted that one of the limitations of this project are the explicit use of secondary data, which can inhibit the outcome of the life cycle assessment.
Hello, my name is Kyle Abbott-Smith, and I'll be introducing a discussion around the parameters that influence the 3D printed building's sustainability impacts. What we have here is an understanding that code-specific variances are a key driver on sustainability impacts of 3D printed buildings. So what I'm saying here is the variances are driven by what we call in the built environment industry the authority having jurisdiction. And so these regulatory mandates their law. And so because this is new, it's a frontier technology, it's one of those things where you've got a technology that is pushing and butting up against what is conventional and known and proposing instead to switch out with something that is in fact unknown. And so it really comes down to providing a body of evidence within academia, within private sector use cases, to drive a change in regulation. And so there's an understanding that a lot of AHJs have not even allowed 3D printed buildings to occur. And where they have, in fact, which is rare within the United States, it's been extremely restrictive. And part of that is just the newness of it, the absence of body of knowledge about the various types of material options that are out there. The relative immaturity in contrast to conventional means and methods of this method of construction. And so here, there's a couple of other sensible elements that go into the regulatory that isn't so much just the risk-averse nature of what the regulators are doing, but instead imply good sense and environmental factors that would have an impact or an influence on sustainability outcomes in 3D printed buildings. The first of which are just very simplistically the seismic activity variances throughout the country. Here, you're thinking about places like San Francisco, where there is high seismic activity, possibility, and potential. And so the codes are commensurately more rigorous and difficult. Sometimes there are some seismic structural attributes that are required there that may not be available within a 3D printed environment. Or, said differently, the components might have to be 3D printed, and so you might back into it in a certain way, but it just depends on what's available within that technology. The next is just sensible climate variances. So, in the north, you're going to be dealing with snow loads. You might have differing levels of precipitation. You've got different types of moisture and humidity within the air that could drive some changes into how the built environment could be designed to withstand those impacts and natural elements, and so then have an impact on how it's designed and in turn the sustainability impacts. And then hurricane wind loads and flood zones and how the buildings would have to be designed to withstand those forces as well. And then the next thing I want to speak about in terms of parameter is the pace of technological change within material science. And so there are a variety of different mediums through which we might achieve a 3D printed building. The first of which I think is commonly well known and often seen when people think about a 3D printed structure, and that is using some kind of a viscous material, very like cement in nature, something that's going to cure and harden into the building fabric or building medium. And so that material, the specification of that material, again relating to codes, to material science development, to availability, that is going to have a huge impact on sustainability impacts of this type of technology. This very much goes to the thinking within the text and the lectures about breaking down and not looking at just the built the building itself, but in fact the units that go into it. And so some kind of a unit view of those materials and how from cradle to grave or cradle to gate or what have you, how the life cycle of those materials, how they contribute to greenhouse gas emissions or other sustainable embodied energy, how those contribute to embodied energy, how those contribute to energy consumption. The entirety of the end-to-end manufacturing cycle for that material will have a great deal of influence on sustainability impacts with this. The other type of medium that we often see here is 3D printed steel buildings or structural elements. So it's not just necessarily the building itself in total, but it could be elements. And you see that where they do these very intricate lattice works with some kind of a steel medium. And what's interesting about that is they can really explore vastly more efficient designs that are using elegant lattice works instead of just a comprehensive, holistic, solid piece of steel. So they can substitute a piece of steel with a lattice work instead, and so may be able to reduce waste material by using those more efficient designs. So it could impact sustainability in that fashion as well. The next thing here, I think, is perhaps the biggest influence on sustainability impacts, and that is the degree to which human beings are integrated into the 3D building process. And I want to talk about this a little bit because it's a practical acknowledgement of the world we live in, that there is a reaction going on to the amount of automation that is occurring within the world. And it's disrupting the status quo within labor markets. You see this readily. Truck drivers and drivers in general are going to be perhaps a first wave of that, where you've got automated trucks and automated freight occurring, and maybe pilots shortly thereafter to follow. And so certainly the construction industry thought it was protected by virtue of the complexity of what it's doing. And we see that the 3D printed building may be one of those things that is attacking that notion that the complexity of the built environment may be something that protects the labor force and the skilled trades from that kind of intrusion of automation into their economic sphere. And so really what I'm saying here is I'm visualizing a scenario where the very organized labor market of the built environment will alter and influence regulations in a way to intentionally put additional workers into the process just to salvage some kind of a foothold and preserve as many jobs as possible as a way to hold on to the old way of thinking. And so in that fashion, there may be some inefficiencies introduced with a thought more towards preservation of economics and wages and labor instead of a preference on and waiting for sustainability. And so that tension is seen often in many places. And so I think that in this field, it's going to be no less different. That one to me is less obvious because it has less to do with the technology and more to do with a trade-offs type of thinking in a more holistic enterprise type of way, beyond the technology itself, beyond the nuts and bolts and means and methods of the material and energy consumption of the 3D printed building itself, and more into the socioeconomic implications of what that technology means. So with that, I will move it on over to the next element of our presentation.
Hello, class. This is our presentation on 3D printed buildings. The section of the program that I received is the opportunities and challenges regarding LCA of 3D printed buildings. Currently, 48% of the total global energy usage annually is attributed to buildings. This includes both the embodied and operating energy Overall, this accounts for approximately 40% of the world's carbon emissions. Even though there has been significant improvements and advancements in construction materials, building systems, and energy modeling, there is a significant challenge to reducing energy and material usage. Additionally, construction of buildings and other infrastructure utilize 25% of our virgin wood, 16% of water, and 40% of sand and gravel each year globally, thus creating large amounts of pollution and waste. The good news, 3D printing is the emerging technology that is reducing energy use and environmental impacts. It has the capability to reduce the amount of materials used, the amount of energy used, equipment use, equipment transportation, and labor. Each one of these items listed above can significantly impact life cycle energy use. Reduced construction materials will be one of the most significant energy and material improvements across all different departments. 3D printing buildings components tend to be smaller in size with better building performance, reducing material use, transportation, and construction. Waste materials. Not only is 3D printing reducing the amount of materials being used, there is also a significant amount of reduction in waste materials generated on the job site. In turn, reduces construction costs and debris removal mitigation. A large portion of products are pre-manufactured to standard sizes and then they are cut on site to meet dimensions. This process creates a waste that isn't usable and sometimes not even recyclable. With 3D printing, materials are created and mixed on demand, and startup and shutdown wastes are eliminated, or at least reduced. This is a huge improvement on the reduction of over-manufacturing and waste for landfills. 3D printing research skill makes use of cementitious materials. New studies are focusing on using natural and locally acquired materials. Locally sourced materials aid with reducing transportation costs, reduce lead times, aid with the construction schedule, and assist with the local job markets and reduce energy consumption and cost as a whole. Natural materials could also reduce the toxicity of built environments. If traditional materials constituting toxic materials are replaced, local materials often suit to the local climate conditions and may also have some of the heating and cooling loads. Save on some of the heating and cooling loads. Discussion of the challenges. The biggest struggles with 3D printing currently is getting engineers involved in locating the sections of their projects where 3D printing can be used to reduce the energy footprints and incorporating them. Change management and adapting to new implementation procedures is a difficult feat. All must embrace the change and work to help reduce the overall impacts. This is a difficult process to overcome. Another big issue is materials and equipment being used in the process. These items are evolving rapidly, and software hardware required to operate the equipment are continually changing. And lastly, getting people trained to operate and maintain the equipment in the emergency career field will require some development, as there has not been many classes generated to create proper certifications to reduce operator error. In conclusion, there are many great benefits to using 3D printing that will greatly reduce the amount of energy in regards to LCA. Not only will it greatly reduce the amount of materials used, it will also reduce the waste and transportation costs. All these things will significantly reduce the amount of energy used in the life cycle of a building. However, there's still going to be a hurdle of getting architects and engineers to incorporate 3D printing into the designs, as well as getting certified operators and companies that can provide the equipment. Even the material design that the printers will be using is still under development and varies greatly depending on the application of your job site. We would expect to see 3D printing process implemented more commonly on job sites over the next 10 years, especially as companies and engineers develop and implement the technologies to be more applicable to modern construction. Thank you.